Hello, my name is Lance Miller, and today I'm going to be looking at the program Desmos and how you can use it in your math classroom. So Desmos is a pretty cool website. Most people think of it as just like graphing, but it's so much more than that. So it's also an app that students can use. Last semester I had my students each had an individual iPad, so they were pretty familiar with using Desmos, and they had that app on there. Um, you can also use your phone to graph, but a lot of the applications and deeper stuff, it's useful to have an iPad or a laptop. So just to go into the graphing part of Desmos, you can just go to desmos.com, and it has a pretty cool graphing feature here that's a lot more user-friendly than a graphing calculator. So for my class, I want to use this. We're going into exponential growth and decay. So it's pretty nice for students to just be able to kind of graph an exponential function like that. This is growth. So they're able to graph it, but one of the cooler features is they're able to add these sliders, they're called. So if I just graph the generic function here, b to the x, you're able to click on add slider, and then from here you can add the slider and play around with that b value. So I'm just going to make it match our parent function here, which is 2 to the x. So b equals 2. So now that we have that, students can play around with this and kind of see what that b value does. So what if we raise 3 to the x or 4 to the x and kind of play, does our y-intercept change? How is the graph transformed from there? So if I set it back down to 2, now I can actually add other sliders to this, including, let's say, like an a value there in front. So the students are familiar with the a, h, k values, but it's kind of cool to visualize and see what they do. So now I can add a slider for the a value here. I'll leave b as 2. That way we're just playing around with one value, one transformation at a time. So now they can see this a value, what that also does to the graph. So I would have students kind of graph the parent function like I'm doing and write in their own words, fill out what each value does to the graph, how it transforms it. That would probably be the best way for them to see rather than just remember, hey, what does the a value do to this graph? They're able to see that as you raise the a value, that's actually a vertical stretch to that exponential graph. So now that's the a and the b value. If I put this back down to match the parent function, I can keep adding sliders. So the next value we can look at is that minus h value and add the slider to that. So when h is 0, it matches our parent function. But as you move h, so it kind of looks like a rope that's kind of rolling up, but that's actually our h value moves the graph left and right. So students are able to see that that is moving the graph left and right. And then the last slider I will add is our k value. And then click on add slider. It starts at 1, so let's make it match the parent function now, and now students can see what that k value does. And I would also ask them, play around with these. What value in this graph is going to be our asymptote, our horizontal asymptote? They should be able to see that because our k value is moving this graph up and down. So if I move the graph 3 units up, that's our k value at 3. No matter what I do to these other values here, that our asymptote is still going to be 3. But no matter what we do here, b value, whether it's growth or decay, our asymptote is still that k value. So this is really useful for the students to kind of visualize the graph and put into their own words what these values do. So another cool feature with Desmos, so I just used to think it was a graphing calculator, and I was like, oh, that's cool enough, but there's actually a lot more that we can do with it. If we go to teacher.desmos.com, oh, it went straight into exponential. So there's actually a lot of activities already in here for your classroom. I've been to a conference where we actually learned to design the activities, and in the future that's something that I would like to look into more. But for now, there's actually already bundles created by teachers that I can use. So I'm going to be doing exponential stuff. So there's actually a lot of bundles in here that we can do with our students. So I've already looked at these. One of the ones that I thought was interesting next is one about tennis here that kind of introduces students to exponential decay. So you can create a class code here and have students join, but I'm going to show you a student preview. So this kind of leads into tennis balls and how they bounce. So this is an example of a good tennis ball here, and it says, what do you think makes a tennis ball bad? I would say it doesn't bounce. So when you submit this as a student, you're also able to see other students' submissions here too. And you, as a teacher, you can actually make it so that a student can't move on until 3 other responses show up here. So they get that instant feedback of other students' answers, so they can kind of compare how they're doing with that. So this continues with an example. Do you think this is good or bad? Bad. It doesn't bounce like we talked about. So, and then as they submit, other answers will pop up so they can continue. The one I wanted to look at though, which kind of leads them to exponential decay, is, let's see here, when they create a bad tennis ball here. So let's take a look. So they're going to create a bad tennis ball with these bounces where the y-axis is the height and the x is the number of bounces, so I'm going to say it doesn't bounce more than twice here. And tell us how you know it's bad. So we'll just kind of let that one go and we'll continue here. So it shows my tennis ball here and it shows the bouncing of it. So it just kind of sits there. So that's how we know it's bad. And now here is where we can kind of see exponential decay. It says that the International Tennis Federation has ruled that tennis balls can't bounce more than 58% or less than 53% of the way to its drop height. So from where it's dropped at, and each continuous bounce, each bounce after that, it can't bounce. It has to be between 53% and 58% of that bounce. So now we have to build our tennis ball based off of that. So when it's dropped 4 feet, it has to bounce up a little more than half its way back up. And same thing, once it comes from 2.2 feet, it has to bounce a little more than half back up. So this is going to get them familiar with that idea of exponential decay, because although it's bouncing about 50% each time, it's 50% off of a lower distance, and that's going to lead us into exponential decay. So I created my tennis ball here, but my second bounce is still too bouncy. So the students have to play around with these values here to make it fit within the parameters. My fourth bounce is a little too bouncy. So it's that idea of exponential growth that this is good for. And let's see, my fourth bounce. So they kind of just play around with this until their values fit. Let's see if I can make a good tennis ball. Just my fifth bounce is wrong now. So once they play with these values, they can kind of see the shape of the graph is an exponential decay, and we created a good tennis ball. So that's one of the features that I like on Desmos. Kind of gets them thinking about what is exponential decay, and that's because our rate is 53 to 58% that it's decaying by each time. There's one last thing I want to show you, which is a little game that has students pair up. So I logged in on 2 different accounts here so that we can show you this game. So student A, which is Jake here, is going to pick any graph. So let's pick this one down here. Next. So the other partner here has to try and figure out which graph Jake picked based on what you can only ask yes or no questions. So this is like that game Guess Who, but for math equations. So I would ask, is the graph exponential? So they can only be yes or no questions, and it automatically, whoever signs into the class code automatically gets paired with another student. So once they're paired, one person will pick a graph, the other one will ask questions. So go back to Jake, he answers the question, is this graph exponential? So yes, it is. So now, based off of my answer, I can eliminate any graphs that are not exponential. Eliminate those. So now I'll ask, is it growth? And the partner over here sees that question and answers yes or no, because you can only answer yes or no. I know the students will want to be like, what graph is it? But they can only answer yes or no. So this is growth, so now the other student can go back and eliminate any graphs that are decay. And a couple more, decay. Alright, so now we are only left with exponential growth. It gets a little trickier to ask yes or no questions. So I would ask, let's see, is the horizontal asymptote 0? And this is the graph I chose, so no, it's not. And then based off that, I can eliminate the ones with the horizontal asymptote. And so on. Let's see here. So we're getting down to where they have to ask harder and harder questions, right? So I can ask, is the y-intercept maybe -4? -4. And this will lead me to the actual graph. Yes, it is. So this partner can see that only one of them, oh, two of them still. All right, so that one's eliminated. So they really have to start asking questions and analyzing these graphs. Is the x-intercept 1? And they will say yes. So now I can eliminate this graph. And we narrowed it down. So we just completed our Guess Who game by analyzing these graphs. So that's just a start in what Desmos can do. This is just exponential functions that I'm using it for, but you can kind of see all the activities that are already built in to this Desmos and all these ones that have already been created. One last thing I wanted to show was how you can go in, once you've created that class code, you can view the dashboard for the assignment here. And this is where all the student answers will come up. So that's the class code for the students. And so here's the student Lance Miller that's completed this. So you can kind of see his answers, which ones he answered, which ones he didn't. So that's a summary. And then as a teacher, you can go to each question. So for this one, he said, when they don't bounce. That's what makes a bad tennis ball. And so you can go into some of the deeper ones. So what do the parameters of the equation mean, and kind of see what each student puts. And if you want to put these on the board as well, you can anonymize the student names. So it'll give Annie Easley just kind of anonymous names, so you can display student answers as well. But you can also get that summary of where each student is, which ones they've answered, and then go into individual questions. So it's really good for you to use it as an assessment for how your class is doing. So that's my overview of Desmos. Good graphing calculator, but there's also a lot more to it. So we have all those activities that I showed you as well, and just nice, easy to use. Hopefully I'll start creating my own someday, but that's Desmos. Thank you.